Tonight, we're going to explore something that feels almost impossible to accept. Time, the one thing that seems most constant in your experience, the steady tick that carries you from moment to moment, might not be as fixed as you think. In fact, according to the deepest physics we know, time can stretch, compress, and under certain extraordinary circumstances, might even allow journeys into both the future and the past. Before we dive in, if you find these quiet explorations of physics meaningful, a gentle like or subscribe helps this channel continue. It's a small gesture, but it allows me to keep making these late night journeys through the cosmos. Now let's begin this careful examination of time itself. Consider what you think you know about time. It flows forward at 1 second per second. Yesterday is gone, tomorrow hasn't happened yet, and right now is the only moment that exists. This seems so obvious that questioning it feels absurd. You wake up, time passes, you go to sleep, the sun rises and sets, clocks tick at their steady pace. Time appears to be the one universal constant, the backdrop against which everything else unfolds. But here's where your intuition starts to fail. Physics tells us that time isn't universal at all. It's personal. Your time and my time don't have to match. The time on your wrist and the time experienced by an astronaut in orbit are genuinely different, not just measured differently, but actually flowing at different rates. This isn't philosophy or speculation. It's measured fact, confirmed by experiments so precise they can detect differences smaller than billionths of a second. The story begins with Albert Einstein working as a patent clerk in Switzerland in 1905. Einstein was thinking about light, about motion, about what it would mean to ride alongside a beam of light traveling through space. His thought experiments led him to a shocking conclusion. The speed of light isn't just fast, it's the speed limit of the universe. Nothing with mass can reach it, and nothing can exceed it. But more importantly for our story, this speed limit has consequences that reach far beyond just limiting how fast spaceships can go. When Einstein worked through the mathematics, he discovered something profound. If the speed of light is the same for everyone, regardless of how fast they're moving, then something else has to give. That something is time itself. Time must slow down for objects moving at high speeds, relative to stationary observers. This isn't just theory anymore. We've measured it. We've seen it in action. Time dilation is as real as gravity or electromagnetism. In 1971, two physicists named Joseph Haefel and Richard Keating decided to test Einstein's predictions in the most direct way possible. They bought airline tickets and took atomic clocks, some of the most precise timekeepers ever built, on trips around the world. These weren't just any clocks. Atomic clocks measure time by counting the vibrations of cesium atoms, and they're accurate to within nanoseconds. When Haefel and Keating returned from their flights, they compared their traveling clocks to identical clocks that had stayed on the ground. The results were exactly what Einstein had predicted. The clocks that had flown eastward, moving with Earth's rotation, had lost time compared to the stationary clocks. The clocks that had flown westward, moving against Earth's rotation, had gained time. The differences were tiny, measured in nanoseconds, but they were real and measurable. Time had actually flowed at different rates for the flying clocks versus the ground-based clocks. This wasn't a malfunction or measurement error. It was time dilation in action. As you listen to this, notice how difficult it is to actually picture this. Your brain wants to reject it because it contradicts everything you've experienced. Time feels absolute, but physics operates beyond the scale of human intuition in realms where everyday experience becomes a poor guide to how reality actually works. The implications extend far beyond airline flights with atomic clocks. Every day, satellites orbiting Earth experience time dilation. The global positioning system in your phone wouldn't work without accounting for these effects. The satellites are moving fast enough and are far enough from Earth's center that their clocks run differently from clocks on the surface. Without correcting for time dilation, GPS would be off by several miles within a few hours. Every time you navigate with your phone, you're relying on Einstein's predictions about the nature of time. But speed isn't the only thing that affects time. Gravity does too, in ways that are even more mind-bending. Einstein realized that gravity doesn't just pull objects together. It actually warps the fabric of space and time itself. The stronger the gravitational field, the slower time flows. This means time passes more slowly on the surface of Earth than it does in orbit, where gravity is slightly weaker. Recent experiments have pushed this measurement to extraordinary precision. Scientists at Gila, a research institute in Colorado, have measured gravitational time dilation across distances as small as a millimeter. They used clouds of ultra-cold atoms as clocks and found that atoms just 1 millimeter higher up experienced time flowing slightly faster than atoms 1 millimeter lower down. The difference was incredibly tiny, about 1 part in 10 to the 19th power, but it was measurable and real. This gravitational time dilation has been confirmed in experiments ranging from the top and bottom of towers to different altitudes on mountains. Every time, the results match Einstein's predictions. Time flows more slowly in stronger gravitational fields. The effect is small on Earth, but it becomes dramatic near extremely massive objects like neutron stars or black holes. Near a black hole, time dilation becomes so extreme that it challenges comprehension. If you could somehow watch someone fall toward a black hole, you would see them appear to slow down as they approached the event horizon. Their movements would become sluggish. Their clock would appear to tick more and more slowly until they seemed to freeze just outside the event horizon. Meanwhile, from their perspective, they would experience time normally as they fell through the event horizon and toward the black hole's center. The universe provides its own demonstration of time dilation through cosmic rays. High in Earth's atmosphere, cosmic ray particles collide with air molecules and create particles called muons. Muons have incredibly short lifespans, about 2.2 microseconds, before they decay into other particles. At the speed of light, 2.2 microseconds is enough time to travel only about 660 meters. Since muons are created about 10 kilometers up in the atmosphere, they shouldn't survive long enough to reach Earth's surface, but they do reach the surface in large numbers. We detect them constantly in radiation detectors on the ground. The reason they survive their journey is time dilation. Because the muons are traveling at speeds very close to the speed of light, their internal clocks run slowly compared to Earth-based observers. What feels like 2.2 microseconds to the muon corresponds to a much longer time from our perspective, long enough for the muon to complete its journey to the ground before decaying. Every muon that strikes a detector on Earth's surface is evidence for Einstein's theory of time dilation. The universe is constantly providing this proof, billions of times per second, as cosmic ray particles stream through our atmosphere. This isn't just an academic curiosity, it's nature demonstrating that time really is relative, that it really does depend on motion and gravity. So far, we've been talking about traveling to the future, which turns out to be relatively straightforward. Speed up or move to a weaker gravitational field, and you'll age more slowly relative to everyone else. When you return, you'll find that more time has passed for them than for you. You'll have traveled into their future. This kind of time travel is not just theoretically possible, it's happening all around us, on small scales. But what about traveling to the past? This is where things become much more speculative and much more strange. Einstein's equations do permit certain exotic solutions that could, in principle, allow backward time travel. These involve concepts with names like closed time-like curves, where the path through space-time loops back on itself, potentially allowing you to return to an earlier time. One possibility involves rotating massive objects. In 1949, mathematician Kurt Gödel found a solution to Einstein's equations that described a universe filled with a rotating fluid. In such a universe, it would be theoretically possible to travel in a loop through space-time and return to your starting point not just in space, but in time. However, this solution doesn't describe our actual universe, which appears to be expanding rather than filled with rotating matter. Another theoretical possibility involves cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe. If cosmic strings exist, and if two of them pass by each other at high speed, the warping of space-time around them could theoretically create closed time-like curves. But cosmic strings remain hypothetical, and even if they exist, engineering such an encounter would be far beyond any conceivable technology. Perhaps the most famous theoretical time machine involves wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or different times. Wormholes arise naturally from Einstein's equations, but they come with a catch. To remain stable and traversable, a wormhole would require something called exotic matter, matter with negative energy density, that would push space-time apart rather than pulling it together. Current models suggest that creating a traversable wormhole would require amounts of exotic matter far exceeding anything we know how to produce. Moreover, even if we could create such exotic matter, the engineering challenges would be staggering. We would need to manipulate the fabric of space-time itself on cosmic scales, something that makes building particle accelerators or landing on Mars look trivial by comparison. You don't need to fully grasp these exotic possibilities. The key point is that while Einstein's equations don't absolutely forbid backward time travel, they make it extraordinarily difficult and may make it impossible under realistic conditions. Every proposed method requires either exotic forms of matter and energy that we've never observed, or conditions so extreme that they may exist only in the most violent corners of the universe. There's also a deeper issue with backward time travel that goes beyond just engineering challenges. If you could travel to the past, you might be able to change events that led to your time travel in the first place. This creates logical paradoxes that have puzzled physicists and philosophers for decades. Perhaps the most famous is the grandfather paradox. If you traveled back in time and prevented your grandparents from meeting, how could you have existed to travel back in time in the first place? Some physicists have proposed solutions to these paradoxes. Maybe the universe would conspire to prevent paradoxes from occurring, a principle called the Novikov self-consistency principle. Maybe time travel to the past is possible, but only in ways that are consistent with what we already know happened. Or maybe attempting to change the past would split the timeline into parallel universes, preserving logical consistency across the multiverse. These remain open questions in theoretical physics. The mathematics of general relativity permits certain forms of backward time travel, but physics doesn't yet have a complete answer about whether such travel is actually possible in our universe. The challenges are not just technological, but may be fundamental to the nature of causality and the structure of space-time itself. It's normal if this feels abstract. Physics often lives beyond intuition, especially when dealing with extreme conditions like black holes, cosmic strings, or the early universe. Our brains evolved to navigate a world of moderate speeds, weak gravity, and familiar timescales. When physics takes us to the edges of space and time, our intuitions become unreliable guides. What we can say with confidence is that time is far stranger and more flexible than our everyday experience suggests. The steady tick of seconds that seems so absolute is actually relative, depending on how fast you're moving and how strong the gravitational field around you happens to be. Every GPS satellite, every cosmic ray muon, every atomic clock experiment confirms that time really is personal, that your time and my time don't have to match. Forward time travel through time dilation is not just possible, but inevitable whenever there's relative motion or differences in gravitational field strength. Backward time travel remains deeply uncertain, permitted by some solutions to Einstein's equations, but requiring conditions so extreme they may be impossible to achieve, or may be forbidden by aspects of physics we don't yet fully understand. As we continue this exploration, we'll delve deeper into the specific mechanisms that make time dilation work, examine the experimental evidence in greater detail, and consider what the malleability of time might mean for the future of human exploration beyond Earth. The story of time is far from over, and the deepest questions about its nature remain tantalizingly open. The mathematics of time dilation become more precise when we examine them closely. When an object moves at high speed relative to a stationary observer, time slows by a factor that physicists call gamma. At everyday speeds, gamma is essentially 1, meaning no noticeable time difference. But as speeds approach the speed of light, gamma grows dramatically. At 90% light speed, time slows by a factor of about 2.3. At 99%, it slows by a factor of 7. At 99.9%, time crawls at about 22 times slower than normal. These numbers aren't just mathematical curiosities. They represent real physical effects that would fundamentally alter human experience at extreme speeds. Imagine accelerating to 99%, the speed of light, and traveling to Proxima Centauri, our nearest stellar neighbor, about 4 light-years away. The journey would take just over 4 years from Earth's perspective, but due to time dilation, you would experience only about 7 months of travel time. You would age 7 months while everyone on Earth aged over 4 years. Return to Earth, and you would have traveled nearly 8.5 years into the future. Your friends would be older, technology would have advanced, the world would have changed in ways you couldn't predict. This isn't science fiction speculation. This is what Einstein's equations tell us would happen, confirmed by every experiment we've conducted on time dilation effects. The energy requirements for such speeds remain staggering by current standards. Accelerating even a small spacecraft to 99% light speed would require more energy than humanity currently produces in decades, but the principle stands. With sufficient energy and engineering capability, dramatic time travel into the future becomes possible through speed alone. Gravitational time dilation offers another pathway to the future, though perhaps even more challenging to exploit. The effect becomes pronounced near extremely massive objects, where space-time curves sharply. Near a neutron star, where gravity is hundreds of billions of times stronger than Earth's, time would pass noticeably slower. An hour near the neutron star's surface might correspond to several hours for distant observers. Black holes represent the extreme case. At the event horizon of a stellar mass black hole, time dilation approaches infinity from an outside perspective. Cross the event horizon, and you would experience time normally while falling toward the center. But external observers would see your image frozen at the horizon, gradually red-shifting and fading as your light struggles against the immense gravitational field. This creates one of physics' most haunting scenarios. From your perspective, you fall through the event horizon in minutes or seconds, experiencing the journey normally until tidal forces tear you apart near the center. But from the outside universe's perspective, you never quite reach the horizon. Your image remains forever frozen at the boundary, slowly fading until it disappears into the darkness. Two equally valid descriptions of the same event, separated by the relativity of time itself. As you contemplate this, notice how the familiar concept of simultaneity starts to dissolve. There's no universal now that applies everywhere in the universe. Your present moment and someone else's present moment, if you're moving relative to each other or experiencing different gravitational fields, don't align. The universe doesn't have a single timeline, but rather a complex web of interconnected time streams, each flowing at rates determined by motion and gravity. This realization extends to astronomical scales in profound ways. When we observe distant galaxies through telescopes, we're seeing them as they existed millions or billions of years ago. Their light has been traveling toward us for eons, carrying information about ancient cosmic history. But due to the expansion of the universe and relativistic effects, determining exactly when those distant events occurred becomes surprisingly complex. Different observers, depending on their motion and location, would assign slightly different times to the same distant astronomical event. The further away the event, the greater these timing discrepancies become. On cosmic scales, the very notion of universal time becomes meaningless. Each location in space-time has its own local time, flowing at rates determined by the gravitational and kinematic environment. Current space missions provide ongoing demonstrations of these effects, though at modest scales. Astronauts aboard the International Space Station experience time dilation due to both their orbital velocity and their distance from Earth's center. The velocity effect makes their clocks run slower, while the gravitational effect makes them run faster. The gravitational effect wins, so astronauts age slightly faster than people on the surface, gaining about 20 milliseconds per year. These small effects accumulate over long-duration missions. Astronauts who spend a full year in orbit return to Earth having aged about 20 milliseconds more than they would have on the surface. It's a tiny difference, but it's real and measurable. As space missions venture further from Earth and travel at higher speeds, these effects will become more pronounced. Future missions to Mars will experience greater time dilation effects. The journey itself, traveling at speeds much higher than orbital velocity, will slow the astronauts' clocks relative to Earth. Time spent on Mars, in a weaker gravitational field than Earth's, will cause their clocks to run slightly faster. When they return to Earth after a multi-year mission, the accumulated time differences could reach several seconds. For missions to the outer solar system, traveling at speeds approaching 1% of light speed using advanced propulsion systems, time dilation could accumulate to minutes or hours over multi-decade journeys. The crews would return to find Earth slightly older than they expected, having experienced their own compressed time stream during the voyage. Interstellar missions would amplify these effects dramatically. Even without approaching relativistic speeds, the immense distances and travel times involved would create significant temporal disconnection between the crew and Earth. A mission to Proxima Centauri using conventional propulsion might take hundreds or thousands of years. Time dilation effects during such a journey would be minimal compared to the journey time itself, but they would still accumulate to measurable differences. More exotic propulsion concepts, like fusion ramjets or antimatter drives, could potentially reach 10 to 20% of light speed. At such velocities, time dilation becomes substantial. A journey to a nearby star system might take several decades from Earth's perspective, but only a few years from the crew's perspective. They would return to find Earth hundreds of years older, having effectively traveled into humanity's far future. The psychological implications of such temporal displacement remain largely unexplored. How would human consciousness adapt to the knowledge that every moment of high-speed travel carries you further into the future of everyone you left behind? What would it feel like to return to an Earth where everyone you knew had died of old age, while you aged only a few years during your journey? Science fiction often glosses over these temporal complexities, but real physics makes them unavoidable. Any future civilization capable of routine interstellar travel would need to grapple with the fundamental loneliness imposed by relativistic time dilation. Crews would become temporal exiles, severed from their origin timeline, not by distance alone, but by the inexorable flow of differential time. Perhaps most unsettling is the realization that we're already experiencing these effects, just at scales too small to notice directly. Every time you drive a car, walk upstairs, or even stand up from a chair, you're creating tiny time dilation effects. The differences are measured in nanoseconds or less, but they're real. Your head experiences time slightly differently from your feet, due to the small difference in gravitational field strength. Your body is not experiencing a single, uniform flow of time, but rather a gradient of slightly different time streams. Modern atomic clocks are sensitive enough to measure these effects directly. Transport an atomic clock from sea level to a mountaintop, and it will gain time relative to an identical clock left at sea level. The difference is small, about 90 nanoseconds per day for a typical mountain, but it's measurable and matches Einstein's predictions exactly. Time really does flow differently at different altitudes, even on Earth. These discoveries force us to reconsider fundamental assumptions about the nature of existence itself. If time is relative, what does it mean for events to be simultaneous? If different observers experience different flows of time, which perspective represents real time? Physics suggests that all perspectives are equally valid, that there's no privileged reference frame from which to judge the correct flow of time. This democratization of temporal perspective has profound philosophical implications. The universe doesn't care about human intuitions regarding time's flow. It operates according to mathematical principles that remain indifferent to our psychological need for universal simultaneity. Each observer carries their own time stream, their own sequence of moments, their own aging process, all equally real within the framework of spacetime. The search for backward time travel pushes these concepts to their theoretical limits. While forward time travel through dilation effects is well established, traveling to the past requires conditions so extreme they may be physically impossible. The proposals that exist in theoretical physics read like catalogs of cosmic impossibilities, rotating black holes, cosmic strings, traversable wormholes, exotic matter with negative energy density. Consider the theoretical construct known as a closed time-like curve. In certain solutions to Einstein's field equations, it becomes mathematically possible to follow a path through space-time that loops back to an earlier time. You could, in principle, meet your younger self or witness events from your own past, but creating such curves would require manipulating the geometry of space-time itself, warping it so severely that cause and effect become circular. The energy requirements for such manipulations dwarf anything in human experience. Creating a traversable wormhole stable enough for time travel would require exotic matter equivalent to the mass energy of entire star systems, precisely arranged and controlled. Even if such matter exists, which remains highly questionable, engineering it into useful configurations would require technology so advanced it approaches the realm of cosmic engineering. Moreover, the mathematics of backward time travel inevitably leads to paradoxes that challenge the logical consistency of the universe itself. If you could travel to the past and change events, you might prevent the conditions that led to your time travel in the first place. This creates logical loops that may be fundamentally incompatible with the causal structure of space-time. Some physicists have proposed that the universe might naturally prevent such paradoxes through mechanisms we don't yet understand, perhaps quantum effects or unknown aspects of gravity would conspire to make backward time travel impossible, even if the mathematics of general relativity appears to permit it. The universe might have built-in safeguards that preserve causality and prevent logical contradictions. Alternatively, backward time travel might be possible, but constrained in ways that preserve consistency. Perhaps you could travel to the past, but only in ways that are consistent with what actually happened. Your actions in the past would be part of the historical record all along, creating a self-consistent timeline where your time travel was always destined to occur. These remain open questions in theoretical physics, touching on fundamental issues about the nature of causality, free will, and the structure of spacetime itself. Current physics cannot definitively answer whether backward time travel is possible, though it suggests that if such travel exists, it would be extraordinarily difficult and might be subject to strict constraints we don't yet understand. The ongoing search for answers drives some of the most sophisticated experiments in modern physics. Particle accelerators push subatomic particles to speeds approaching the speed of light, creating controlled environments where time dilation effects become pronounced. These experiments continuously confirm Einstein's predictions while searching for any deviations that might point toward new physics. Gravitational wave detectors, like LIGO, have opened new windows into extreme gravitational environments where space-time itself becomes dynamic. When black holes collide billions of light years away, they send ripples through space-time that we can detect on Earth. These waves carry information about conditions so extreme that time and space become fluid, warping and oscillating in ways that would have seemed impossible just decades ago. Future experiments will push these boundaries further. Advanced atomic clocks will measure time dilation effects with ever greater precision, potentially revealing subtle deviations from Einstein's predictions that could point toward a more complete understanding of space-time. Space-based gravitational wave detectors will observe cosmic collisions with unprecedented sensitivity, probing the behavior of time and gravity in the most violent events the universe produces. The practical applications of our growing understanding of time continue to expand. Beyond GPS corrections and particle physics experiments, precise timekeeping enables technologies from high-frequency trading to synchronized power grids to fundamental research in astronomy and physics. As our clocks become more accurate, we become more sensitive to the subtle ways that time varies across different environments. Perhaps most remarkably, our understanding of time's flexibility opens conceptual doorways to futures we can barely imagine. If humanity ever develops the technology for routine interstellar travel, time dilation will become a central aspect of the human experience. Travelers will age differently from those who remain behind, creating complex social and psychological challenges that no previous generation has faced. The descendants of today's space explorers might become temporal nomads, moving between star systems while experiencing compressed time streams relative to planetary populations. They might measure their lives not just in years, but in reference frames, maintaining connections across vast distances and time differences through technologies we cannot yet envision. Current physics provides the mathematical framework for such possibilities, while remaining honest about their extraordinary challenges. The speed of light remains a fundamental barrier that shapes the possible futures of any spacefaring civilization. Even with perfect technology, the universe imposes travel times that create unavoidable temporal separations between distant communities. Yet these limitations also create opportunities for experiences unknown in human history. Time dilation could allow individual humans to witness cosmic evolution across timescales normally reserved for geological processes. A sufficiently long journey at high speeds could let someone experience the aging of star systems, the collision of galaxies, or the long-term evolution of the cosmos itself. The universe reveals itself as far stranger and more malleable than everyday experience suggests, while remaining bound by mathematical laws that operate with perfect consistency across all scales and conditions. Time emerges not as the fixed backdrop of existence, but as a dynamic dimension of reality, flowing at rates determined by motion and gravity, carrying each observer along their own unique path through the unfolding moments of spacetime, E-time. The strange reality about time manipulation extends beyond just theoretical curiosities into technologies we might actually build within this century. Proposed fusion rockets could accelerate spacecraft to perhaps 5% of light speed, creating time dilation factors large enough to notice during a human lifetime. A journey to Alpha Centauri at such speeds would take about 90 years from Earth's perspective, but the crew would experience roughly 85 years due to time dilation effects. Not dramatic by science fiction standards, but real enough to create measurable temporal displacement between the travelers and everyone they left behind. More exotic propulsion concepts push these effects further into the realm of genuine time travel. Antimatter engines, if we ever learn to produce and store antimatter safely, could theoretically accelerate spacecraft to 20 or 30% of light speed. At such velocities, time dilation becomes substantial enough to compress decades of travel time into years of experienced time. The crew would return to find Earth generations older while they aged only a fraction of the expected journey time. Notice how this creates an irreversible form of temporal exile. Unlike the reversible time travel of science fiction, relativistic time dilation offers only one-way passage into the future. There's no return ticket to your original timeline, no way to undo the temporal displacement. Every moment of high-speed travel carries you further into the future of everyone you knew, creating a form of loneliness that no previous generation of humans has ever experienced. The mathematics become more precise when we examine specific scenarios. Consider a spacecraft accelerating continuously at 1 Earth gravity, a comfortable acceleration for human passengers that would feel like normal weight throughout the journey. After 1 year of such acceleration, the spacecraft would reach about 97% of light speed, and time dilation effects would become dramatic. What feels like additional months to the crew would correspond to years passing on Earth. Continue this acceleration profile, and the effects compound exponentially. A journey that takes 5 years of ship time could correspond to centuries passing on Earth. The crew would emerge into a future where their civilization had evolved beyond recognition, where their language might be archaic, where their memories would represent historical curiosities rather than living connections to contemporaries. Current physics places fundamental limits on how extreme these effects can become. As spacecraft approach light speed, the energy required to accelerate further increases without bound. Reaching exactly light speed would require infinite energy, making it impossible for any object with mass. This means there's a practical upper limit to how much time dilation any realistic spacecraft could achieve, even with perfect technology. But even these limits permit time dilation factors of hundreds or thousands. A spacecraft traveling at 99.9% of light speed experiences time flowing about 22 times slower than Earth-based observers. A journey that takes 20 years of ship time would correspond to more than 4 centuries passing on Earth. The crew would travel nearly half a millennium into the future during what felt like a normal career-length voyage. As you consider these possibilities, notice how they challenge basic assumptions about human continuity across time. We think of ourselves as part of ongoing civilizations, connected to past and future through cultural transmission and shared history. But relativistic time travel could sever those connections permanently, creating temporal refugees displaced from their own species' timeline. The energy requirements for such journeys remain staggering by contemporary standards. Accelerating even a modest spacecraft to 99% of light speed would require more energy than human civilization currently produces in years or decades. The fuel alone, whether fusion plasma or antimatter, would need to be manufactured and stored in quantities that dwarf any industrial project ever attempted. Yet the principles remain sound. The physics works. The engineering challenges are enormous, but not necessarily impossible. Future civilizations, with access to stellar-scale energy sources, might routinely send expeditions into their own far futures, exploring not just distant space, but distant time as well. This brings us to one of the more haunting aspects of our universe's structure. The speed of light doesn't just limit how fast we can travel through space. It fundamentally constrains how civilizations can interact across cosmic distances. Even signals traveling at light speed take years to reach nearby stars and millennia to cross galactic distances. Any message sent to a civilization orbiting another star becomes a communication with the past by the time it arrives. A conversation with aliens 10 light years away would require 20 years for each exchange of ideas. By the time they respond to your question, you might have forgotten asking it. Such communications would resemble exchanges between archaeologists studying ancient civilizations rather than dialogues between contemporaries. The isolation becomes even more profound when we consider that any spacefaring civilization would face the same relativistic constraints we do. If they visited Earth traveling at high relativistic speeds, they would experience their own time dilation effects. They might arrive having aged only years, while decades or centuries passed in their home system. They would be temporal exiles from their own civilization, carrying knowledge and perspectives from a past their contemporaries had moved beyond. This suggests that the universe might be filled with temporal refugees, individuals, and crews displaced from their original timelines by the necessities of interstellar travel. Each journey between stars could create new temporal orphans, beings who exist out of sync with both their origin and destination civilizations. The psychological implications remain largely unexplored because we have no precedent for such experiences in human history. How would consciousness adapt to the knowledge that every moment of travel carries you irreversibly into the future? What would it feel like to return home and discover that everyone you knew had died of old age while you aged only a few years? Perhaps more unsettling is the realization that this temporal isolation isn't just a consequence of extreme technology. It's built into the fundamental structure of space-time itself. The universe appears designed to prevent easy communication or travel across large distances, imposing temporal barriers that make cosmic civilizations naturally isolated from each other in time as well as space. These barriers might explain why we haven't detected signals from other technological civilizations. It's not just that space is vast, it's that any civilization capable of interstellar communication or travel would quickly become temporally fragmented, with different groups aging at different rates and losing synchronization with each other. A galaxy full of intelligent life might be a galaxy full of temporal exiles, each group isolated in their own time stream. The search for solutions to these temporal constraints drives some of the most exotic research in theoretical physics. Scientists explore concepts like traversable wormholes that could theoretically provide shortcuts through spacetime, allowing rapid travel between distant regions without the time penalties imposed by relativistic effects. But every proposed solution comes with extraordinary requirements. Wormholes would need to be stabilized using exotic matter with properties unlike anything we've observed. The amounts required would be staggering, possibly equivalent to the mass energy of entire solar systems. Even if such matter exists, controlling it with sufficient precision to maintain a stable wormhole would require engineering capabilities that approach the realm of cosmic scale construction projects. Alternative approaches focus on manipulating spacetime itself. The Alcubierre warp drive concept proposes contracting space in front of a spacecraft while expanding it behind, allowing the ship to effectively travel faster than light without violating relativity. The spacecraft would remain in a region of flat spacetime, avoiding time dilation effects entirely. But this approach faces similar obstacles. Creating and controlling the required spacetime distortions would demand exotic matter with negative energy density, arranged in precise configurations around the spacecraft. Current estimates suggest that energy requirements would exceed the total mass energy of observable matter in the universe, making such drives effectively impossible with any conceivable technology. It's worth pausing to consider how these limitations reflect deeper truths about the nature of our universe. The speed of light isn't just a speed limit, it's a fundamental constant that shapes the possible forms of cosmic civilization. Any species that develops interstellar travel must confront the same temporal barriers we face. The universe seems structured to prevent easy communication across large scales, creating natural isolation that might be an inescapable feature of cosmic evolution. This isolation might actually be necessary for the development of diverse civilizations. If instant communication across galactic distances were possible, dominant civilizations might suppress the development of independent cultures on distant worlds. The temporal barriers imposed by light speed could serve as protective mechanisms, ensuring that each world has time to develop its own unique approaches to existence before encountering other forms of intelligence. Current research continues pushing against these barriers while respecting their fundamental nature. Advanced propulsion concepts explore the theoretical limits of what might be achievable within known physics. Ion drives, fusion rockets, and even speculative antimatter engines could potentially reach significant fractions of light speed, creating substantial time dilation effects for future space travelers. Breakthrough Starshot, an actual research program, proposes accelerating tiny spacecraft to 20% of light speed using powerful ground-based lasers. These probes would be far too small to carry humans, but they demonstrate that achieving relativistic speeds isn't necessarily impossible. The probes would reach nearby star systems in decades rather than millennia, though they would still face the one-way nature of relativistic travel. Scaling such concepts to human-carrying spacecraft remains extraordinarily challenging. The energy requirements increase dramatically with spacecraft mass, and human passengers require life support systems, radiation shielding, and living space that multiply the engineering difficulties. But the fundamental physics remains permissive. With sufficient energy and engineering capability, sending humans on relativistic journeys becomes possible in principle. The deeper question is whether any civilization would choose such isolation. Knowing that relativistic travel creates permanent temporal displacement, would humans or other intelligent species accept the loneliness of becoming unstuck from their own timelines? The answer might depend on how we value exploration versus connection, discovery versus continuity. Perhaps the most profound insight from studying time's malleability is how it reveals the universe's indifference to human intuitions about causality and sequence. We think of time as the universal organizing principle, the dimension along which cause precedes effect and past determines future. But physics shows us that time is just another coordinate in spacetime, as flexible and relative as spatial dimensions. This flexibility extends to our understanding of cosmic history itself. When we observe distant galaxies through telescopes, we see them as they existed millions or billions of years ago. But determining exactly when those distant events occurred becomes surprisingly complex when we account for relativistic effects. Different observers, depending on their motion and gravitational environment, would assign slightly different timestamps to the same cosmic events. The expansion of the universe adds another layer of temporal complexity. As space stretches between galaxies, it carries them apart at speeds that can exceed the speed of light for sufficiently distant objects. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Instead, space itself is expanding, creating distance faster than light can traverse it. This expansion creates cosmic horizons beyond which we can never communicate, regardless of how long we wait or how advanced our technology becomes. Galaxies beyond a certain distance are receding so fast that signals we send toward them will never arrive. We exist in a bubble of possible communication that encompasses only a tiny fraction of the total universe. Within this bubble, time flows differently for every observer, depending on their motion and location. The universe has no master clock, no universal now that applies everywhere simultaneously. Each point in space maintains its own local time, flowing at rates determined by the gravitational and kinematic environment. What we call the present moment is actually a complex collection of different local times, synchronized only approximately and only within limited regions. These realizations force us to reconsider fundamental assumptions about existence, causality, and the nature of reality itself. If time is relative and flexible, what does it mean for events to be simultaneous? If different observers experience different sequences of events, which perspective represents objective reality? Physics suggests that all perspectives are equally valid, that the universe operates without regard to any privileged reference frame or absolute timeline. This democratization of temporal perspective has a profound philosophical implications that extend far beyond physics. It suggests that reality itself is more complex and nuanced than our evolved intuitions can easily grasp. We live in a universe where time is personal, where each observer carries their own sequence of moments, where the flow of existence varies depending on motion and gravity in ways that challenge our deepest assumptions about the nature of being. Yet this same flexibility opens possibilities we're only beginning to explore. Understanding time's malleability could guide the development of technologies that let future humans experience time in ways their ancestors never imagined. Controlled time dilation could allow individuals to witness cosmic evolution across vast timescales, or to synchronize with distant civilizations despite the light speed delays that separate them. The universe emerges as stranger and more subtle than everyday experience suggests, operating according to principles that remain indifferent to human preferences while offering opportunities for experiences that transcend ordinary temporal existence. Time reveals itself not as the fixed stage upon which events unfold, but as another dimension of reality, as malleable as space itself, flowing at rates that depend on the observer's journey through the vast, quiet expanse of spacetime. The engineering challenges we've been exploring represent only part of the story. There's something deeper at work here, something that reveals itself when we examine not just the mechanics of time travel, but the quantum foundations that might ultimately determine what's possible and what isn't. The universe operates according to principles that extend far beyond the smooth, continuous spacetime that Einstein described. At the smallest scales, where particles flicker in and out of existence, and uncertainty becomes a fundamental law, the nature of time itself takes on qualities that challenge even our most sophisticated theories. Consider the vacuum of empty space. Your intuition tells you that empty space contains nothing, that it's simply an absence waiting to be filled. But quantum mechanics reveals something profoundly different. What we call empty space seethes with activity at scales far below anything we can directly observe. Virtual particles constantly appear in pairs, exist for impossibly brief moments, then annihilate each other and disappear. This isn't speculation, it's a prediction of quantum field theory that has been confirmed through measurable effects like the Casimir force, where two metal plates placed extremely close together in vacuum experience an attractive force caused by the quantum fluctuations of empty space itself. These quantum fluctuations might hold the key to understanding whether exotic matter, the hypothetical substance required for traversable wormholes and backward time travel, could ever exist in sufficient quantities. Current calculations suggest that quantum effects could theoretically produce small amounts of negative energy density under very specific conditions. The Casimir effect demonstrates that quantum vacuum can indeed exhibit properties that classical physics would consider impossible, including regions where the energy density becomes negative relative to the surrounding vacuum. But the amounts involved are staggering in their smallness. The negative energy density produced by the Casimir effect between two perfectly conducting plates separated by a micrometer, is about -1 joule per cubic kilometer. To stabilize even a microscopic wormhole would require negative energy densities billions of times larger, sustained across volumes far exceeding anything we could engineer. The gap between what quantum mechanics permits and what practical wormhole construction would require remains almost incomprehensibly vast. This brings us to one of the most subtle aspects of time's relationship with quantum mechanics. In quantum field theory, particles don't have definite positions or trajectories until they're measured. Instead, they exist in superpositions of all possible states with probabilities that evolve according to mathematical equations that govern the quantum realm. But time appears differently in this quantum description. While spatial coordinates become fuzzy and probabilistic, time often maintains its classical character as a parameter that describes how quantum states evolve. This asymmetry between time and space at quantum scales hints at something profound about time's fundamental nature. Perhaps time really is more basic than space, serving as the stage upon which quantum events unfold, rather than being just another coordinate that can be manipulated like spatial dimensions. Or perhaps our current theories are incomplete, missing some deeper principle that would unify time and space even at quantum scales. The question becomes more pointed when we consider quantum entanglement, the phenomenon where particles become correlated in ways that seem to transcend normal limitations of space and time. When two particles become entangled, measuring one instantaneously affects the other, regardless of the distance separating them. This effect has been confirmed across distances of hundreds of kilometers and shows no sign of weakening with distance. The correlation appears to occur faster than light could travel between the particles, suggesting some form of connection that operates outside normal spacetime constraints. Einstein famously called this spooky action at a distance and thought it revealed problems with quantum mechanics rather than genuine features of nature. But decades of experiments have confirmed that quantum entanglement is real and operates exactly as quantum theory predicts. The particles don't send signals to each other in any conventional sense. Instead, they share a quantum state that transcends their spatial separation, existing as a single system despite being physically distant. As you contemplate this, notice how it challenges intuitions about locality and causality. If entangled particles can affect each other instantaneously across arbitrary distances, what does this mean for the structure of spacetime? Some physicists have proposed that entanglement might represent a more fundamental level of reality than spacetime itself, with space and time emerging as approximate descriptions of deeper quantum connections. This perspective suggests that our current understanding of time travel limitations might be incomplete. If spacetime emerges from quantum entanglement, then perhaps manipulating quantum correlations could provide pathways through time that classical general relativity cannot access. But such possibilities remain deeply speculative, requiring advances in quantum gravity theory that may be decades or centuries away. The intersection of quantum mechanics and gravity remains one of physics' most challenging frontiers. We know that quantum effects become important at the Planck scale, about 10 to the negative 35 meters, where the uncertainty principle makes the very concept of smooth spacetime break down. At these scales, space and time themselves might become quantized, existing in discrete units rather than forming the continuous fabric that general relativity describes. Some theories suggest that time might be emergent rather than fundamental, arising from more basic quantum processes, in the same way that temperature emerges from the motion of molecules. In this view, what we experience as the flow of time could be a statistical phenomenon, a consequence of the universe evolving from ordered states toward maximum entropy. The arrow of time that gives us a sense of past and future might not be built into the fabric of space-time, but might instead emerge from the collective behavior of quantum systems. This thermodynamic arrow of time creates its own puzzles for time travel scenarios. Even if the equations of physics permit backward time travel, the statistical tendency toward increasing entropy might make such travel practically impossible. Traveling to the past would require decreasing entropy, organizing matter and energy in ways that violate the statistical principles governing large systems. The universe's natural tendency toward disorder might serve as a barrier against paradoxes, making backward time travel self-limiting, even if it's theoretically permitted. These considerations extend to the information paradoxes we encounter in extreme gravitational environments. When matter falls into a black hole, quantum mechanics insists that the information it carries must be preserved in some form. But general relativity suggests that information falling past the event horizon is lost forever. This conflict between quantum mechanics and gravity points toward gaps in our understanding that might be crucial for determining whether backward time travel is truly possible. Recent work on black hole physics suggests that information might be preserved through subtle correlations between the black hole's interior and the Hawking radiation it emits. If this is true, then black holes might not destroy information, but rather encode it in forms so scrambled that recovering it would require measurements of extraordinary precision extended over vast periods of time. This holographic encoding of information might represent a general principle that governs how the universe preserves causality, even in extreme circumstances. The holographic principle itself offers hints about the nature of space-time that could be relevant to time travel. This principle suggests that all the information contained in a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. If space-time is holographic, then what we perceive as three-dimensional space plus time might be a projection of information encoded on distant boundaries. This perspective makes the interior of space-time somewhat illusory, a convenient description that emerges from more fundamental information processing on the boundaries. In such a framework, time travel might not involve moving through space-time, but rather accessing different aspects of the information encoded on cosmic boundaries. Such access might be possible in principle, but limited by the computational resources required to decode and navigate the holographic information. Current experiments in quantum mechanics continue revealing new aspects of how time and information interact at fundamental levels. Quantum computers, which manipulate quantum superpositions and entanglement to perform calculations, demonstrate that quantum systems can indeed access computational pathways that classical systems cannot. While these machines don't enable time travel in any direct sense, they show that quantum mechanics permits forms of information processing that transcend classical limitations. The development of quantum technologies might eventually provide tools for probing the relationship between time, information, and space-time in ways we cannot currently achieve. Quantum sensors can already measure gravitational effects with extraordinary precision, detecting changes in space-time curvature that would have been impossible to observe just decades ago. Future quantum technologies might reveal subtle aspects of time's structure that our current theories miss. Perhaps most intriguingly, some theoretical work suggests that consciousness itself might play a role in how quantum systems evolve through time. This doesn't mean that consciousness controls quantum mechanics in any mystical sense, but rather that the act of observation or measurement might be more fundamental to the structure of space-time than classical physics assumed. If consciousness and quantum measurement are intimately connected to how time unfolds, then understanding time travel might require understanding consciousness itself. The relationship between mind and time has puzzled philosophers and scientists for centuries. We experience time as flowing from past to future, with memories of the past and anticipations of the future creating our sense of temporal continuity. But physics describes time as just another coordinate, with no inherent direction or flow. The subjective experience of time's passage might be a feature of how conscious systems process information rather than a property of time itself. This suggests that any form of time travel would need to account not just for the physics of moving through space-time, but for how consciousness would experience such movement. Would traveling to the past preserve memories of the original timeline? Would the traveler experience multiple overlapping time streams? These questions touch on deep issues about the nature of personal identity and continuity that go beyond physics into philosophy and neuroscience. The practical implications of quantum effects on time travel scenarios remain largely unexplored because the relevant scales are so far beyond current experimental reach. But some effects might be observable in principle. Quantum fluctuations in space-time could create microscopic, closed, time-like curves that last for infinitesimally brief periods. These quantum time loops would be far too small and short-lived to allow macroscopic time travel, but they might be detectable through their effects on quantum field fluctuations. Detecting such effects would require instruments sensitive enough to measure quantum space-time fluctuations, technologies that push far beyond current capabilities. But the theoretical framework exists for predicting what such fluctuations should look like, providing targets for future experiments that might reveal how quantum mechanics and gravity interact at fundamental scales. The search for quantum gravity effects drives some of the most ambitious experimental programs in modern physics. Gravitational wave detectors, like LIGO, have already revealed that space-time can oscillate and carry information across cosmic distances. Future detectors with even greater sensitivity might detect quantum effects in gravitational waves, revealing how space-time behaves when quantum mechanics and gravity both become important. Space-based experiments could probe these effects in environments impossible to create on Earth. Satellites carrying ultra-precise atomic clocks could measure how quantum effects influence time dilation in ways that ground-based experiments cannot access. The microgravity environment of space provides natural laboratories for studying how quantum systems behave in varying gravitational fields, potentially revealing connections between gravity and quantum mechanics that remain hidden in terrestrial experiments. These research directions converge on fundamental questions about the nature of reality itself. If time is emergent rather than fundamental, if space-time is holographic rather than literal, if consciousness plays a role in how quantum systems evolve through time, then our current understanding of time travel limitations might be missing crucial aspects of how the universe actually works. The answers to these questions will likely require theoretical breakthroughs that unify quantum mechanics and gravity in ways we cannot currently achieve. String theory, loop quantum gravity, and other approaches to quantum gravity each offer different perspectives on how time might behave at fundamental scales. None of these theories is yet complete or confirmed, but each suggests that time's true nature might be far stranger than either classical physics or quantum mechanics alone would suggest. What emerges from this exploration is a picture of time as perhaps the most mysterious aspect of physical reality. Unlike space, which we can move through freely in any direction, time seems to impose a preferred direction that aligns with the increase of entropy and the subjective flow of consciousness. Unlike matter and energy, which are conserved, time seems to be created continuously as the universe evolves and expands. These asymmetries hint that time might occupy a special place in the fundamental structure of reality, serving as the stage upon which quantum and gravitational processes unfold, rather than being just another coordinate that can be manipulated arbitrarily. If this is true, then time travel limitations might reflect deep principles about causality and information that transcend the specific equations of general relativity or quantum field theory. The universe appears to be structured in ways that make forward time travel through dilation effects inevitable, while making backward time travel extraordinarily difficult and possibly impossible. This asymmetry might not be accidental, but might instead reflect fundamental principles about how information and causality operate in physical systems. The arrow of time that gives us our sense of past and future might be woven into the very foundations of physical law. Current physics provides a framework for understanding these limitations while remaining honest about the vast territories of ignorance that surround our knowledge. We can calculate time dilation effects with extraordinary precision and predict how massive objects warp spacetime, but we cannot yet describe how quantum mechanics and gravity interact at the smallest scales where time's true nature might be revealed. The search continues through both theoretical work and increasingly sophisticated experiments. Each measurement of time dilation effects, each detection of gravitational waves, each advance in quantum technology brings us closer to understanding how time really works at the deepest levels of physical reality. The story of time reveals itself as perhaps the most human of all physics stories. We are creatures who exist in time, who experience its passage, who remember the past and anticipate the future. Our consciousness seems intimately connected to time's flow in ways we're only beginning to understand. Any complete theory of time we'll need to account not just for how clocks tick, but for how minds experience the ticking. Perhaps the deepest insight from studying time's malleability is how it reveals the universe's profound indifference to human desires while simultaneously creating the conditions that make human experience possible. The same relativistic effects that make interstellar travel lonely and difficult also enable the formation of stable matter and the evolution of complex structures like planets and life. Time dilation that separates space travelers from their home timelines also allows the universe to evolve from simple initial conditions to the rich complexity we observe around us. The universe unfolds according to mathematical principles that operate without regard to human hopes or fears. Yet these same principles create spaces where hope and fear can exist, where consciousness can emerge and contemplate its own place in the vast, quiet expanse of spacetime that stretches from the smallest quantum fluctuations to the largest cosmic structures, all flowing together through the mysterious dimension we call time. The most intriguing aspect of time manipulation might not be the exotic scenarios we've been exploring, but something far more accessible that's happening around you right now. Every atom in your body carries within it a natural clock, ticking at frequencies determined by the fundamental forces that hold matter together. These atomic timepieces are so precise that they reveal time variations we could never sense directly, changes that occur simply from moving through the everyday world in ways that feel perfectly ordinary. Consider the atomic clocks aboard GPS satellites orbiting overhead as you listen to this. These instruments measure time by counting the oscillations of cesium atoms, tracking frequencies so stable that they maintain accuracy to within nanoseconds over periods of years. Yet even these extraordinary timepieces require constant correction for relativistic effects. The satellites move fast enough and orbit far enough from Earth's center that their clocks run differently from identical instruments on the ground. Without accounting for these differences, your phone's navigation would drift by several miles within hours. The corrections happen automatically, invisibly, every time you check your location or follow directions. You're relying on Einstein's predictions about time's flexibility without thinking about it, using technology that would fail completely if time were truly universal and absolute. The GPS satellites demonstrate that time dilation isn't just a theoretical curiosity, but a practical necessity for technologies we use every day. This reveals something profound about our relationship with physics. We live embedded in a universe governed by principles that operate far beyond human intuition, yet we've learned to work with these principles so seamlessly that we forget how strange they really are. The same relativistic effects that enable GPS navigation also govern the behavior of every fast-moving particle in the cosmic ray showers constantly raining down through the atmosphere. So, as you sit listening to this, cosmic ray muons created 10 kilometers above your head are completing their journey to Earth's surface, surviving only because time dilation extends their brief lifespans from our reference frame. These particles experience time normally from their own perspective, but their high-speed motion slows their internal clocks relative to Earthbound observers. What should be a fatal journey lasting many times their natural lifetime becomes a routine transit they complete easily. Every muon detection in atmospheric research laboratories provides evidence for time's flexibility. Every GPS correction confirms that time flows differently for moving observers. Every atomic clock experiment reveals variations in time's passage that occur simply from changes in altitude or velocity too small for human senses to detect. The universe continuously demonstrates that time is personal, relative, flowing at rates determined by motion and gravity in ways that challenge our most basic assumptions about temporal experience. The precision of modern atomic clocks has reached levels where they can detect gravitational time dilation across vertical distances measured in centimeters. Transport one of these instruments from the ground floor to the top floor of a typical building, and it will gain time relative to an identical clock left below. The difference amounts to only a few parts, in 10 to the 17th power, but it's measurable and real. Time genuinely flows faster at higher altitudes where Earth's gravitational field is slightly weaker. Notice how this forces us to reconsider what we mean by simultaneous events. If time flows at different rates depending on altitude, motion, and gravitational environment, then there's no universal moment that applies everywhere at once. Your head experiences time slightly differently from your feet due to the small difference in gravitational field strength across your height. The effect is far too small to sense directly, but it's present and measurable with sufficiently precise instruments. This fragmentation of simultaneity becomes more pronounced across larger scales. An event occurring on the Sun and an event occurring on Earth cannot be simultaneous in any absolute sense because of the different gravitational environments and the finite speed at which information can travel between them. What counts as now depends on where you are and how you're moving through spacetime. The implications extend to our understanding of cosmic history itself. When we observe distant galaxies through telescopes, we see them as they existed millions or billions of years ago when their light began its journey toward us. But determining exactly when those ancient events occurred becomes surprisingly complex when we account for the expansion of space and relativistic effects. Different observers would assign slightly different timestamps to the same distant cosmic events, depending on their motion and gravitational environment. This temporal complexity compounds as we look deeper into space and further back in time. The most distant galaxies we can observe existed when the universe was only a few 100 million years old, less than 5% of its current age. Their light has been traveling toward us for over 13 billion years, carrying information about cosmic conditions from an era when the first stars were just beginning to illuminate the primordial darkness. During this vast journey, space itself has been expanding, stretching the wavelengths of the ancient light and carrying the source galaxies to distances far greater than when they emitted the photons we now detect. The galaxies we see in deep space images no longer exist in the locations where we observe them. They've been carried away by cosmic expansion to regions beyond our current observational horizon. This creates a strange temporal landscape where the past remains visible while the present becomes increasingly inaccessible. We can study the universe as it existed billions of years ago by looking at distant galaxies, but we cannot observe those same galaxies as they exist today because their current light hasn't had time to reach us yet. The deeper we look into space, the further we see into the past, creating a natural time machine that reveals cosmic history but hides cosmic present. As you contemplate this, notice how it challenges intuitions about existence and persistence. The galaxies we study in deep space surveys might have evolved beyond recognition or might no longer exist at all in their current state. We're studying archaeological remnants of cosmic structures preserved in light that has been traveling toward us for eons while the sources themselves evolved or disappeared. This archaeological aspect of astronomy extends to every scale of cosmic observation. The light from nearby stars is minutes or years old when it reaches us. The light from distant planets in our solar system is hours old. Even the light reflecting from the moon is over a second old by the time it enters our eyes. We never see the universe as it is, only as it was, with delays determined by the finite speed of light and the vast distances separating celestial objects. Current research pushes these temporal investigations into increasingly exotic regimes. Gravitational wave detectors like LIGO can observe the final moments of black hole mergers that occurred billions of years ago and billions of light years away. These observations reveal how space-time itself behaves when subjected to the most extreme gravitational conditions the universe produces. When two black holes spiral together and merge, they create ripples in space-time that propagate outward at the speed of light. These gravitational waves carry information about the collision encoded in the precise pattern of space-time stretching and compression. By the time the waves reach Earth, they've traveled across cosmic distances while preserving detailed information about events that lasted only seconds but released more energy than all the stars in the observable universe were emitting simultaneously. The detection of these waves required instruments sensitive enough to measure changes in distance, smaller than 1/10,000th the width of a proton. The LIGO detectors accomplish this by bouncing laser light back and forth along arms several kilometers long, monitoring how gravitational waves alternately stretch and compress the space through which the light travels. When a gravitational wave passes through the detector, it changes the round-trip travel time of the laser light by amounts so small they approach the fundamental quantum limits of measurement precision. These measurements reveal that space-time itself can oscillate, carrying information across cosmic distances through the fabric of reality rather than through electromagnetic radiation. Gravitational waves represent a form of cosmic communication that operates through the geometry of space-time itself, providing information about events so violent they would destroy any material probe sent to observe them directly. Future gravitational wave observatories will extend these capabilities into space, using spacecraft separated by millions of kilometers as the arms of interferometers sensitive to much longer wavelength gravitational waves. These space-based detectors will observe the inspiral and merger of supermassive black holes at galactic centers, events that occur over periods of months or years, rather than the seconds-long mergers that ground-based detectors observe. The development of increasingly sophisticated time measurement and space-time detection technologies continues revealing new aspects of temporal reality that remained hidden until recently. Quantum sensors can now measure gravitational effects with precision that would have seemed impossible just decades ago. These instruments probe the intersection between quantum mechanics and gravity in regimes where both become important for understanding how space-time behaves at fundamental scales. Some of the most intriguing current research focuses on how quantum entanglement might relate to the structure of space-time itself. When particles become quantum mechanically entangled, they share correlations that persist regardless of the distance separating them. Measuring one entangled particle instantaneously affects the quantum state of its partner, creating connections that appear to transcend normal spacetime limitations. This quantum connectivity might represent a more fundamental level of reality than the spacetime coordinates we use to describe particle locations. Some theoretical work suggests that spacetime itself might emerge from quantum entanglement patterns, with the familiar three dimensions of space plus time arising as approximate descriptions of deeper quantum correlations between fundamental information processing units. If this perspective proves correct, then our understanding of time travel limitations might be incomplete. The barriers imposed by light speed and the exotic matter requirements for wormhole stabilization might reflect limitations of our current space-time description rather than fundamental constraints on how information and causality operate at the deepest levels of reality. But such possibilities remain deeply speculative, requiring theoretical advances that may be decades or centuries away. Current physics provides a framework for understanding time's malleability within the context of general relativity and quantum mechanics as we currently understand them, while remaining honest about the vast territories of ignorance surrounding questions about quantum gravity and the fundamental nature of spacetime. The practical implications of our growing understanding of time continue expanding into technologies that would have seemed like magic to previous generations. Atomic clocks now achieve precision sufficient to test general relativity in Earth-based laboratories, measuring gravitational time dilation effects that occur over distances measured in meters rather than astronomical units. These ultra-precise timepieces enable new forms of fundamental research that probe the intersection between quantum mechanics and gravity. By comparing atomic clocks at different altitudes or accelerations, researchers can test whether quantum systems experience gravitational effects in ways that match Einstein's predictions or reveal deviations that might point toward new physics. The search for such deviations drives some of the most sensitive measurements ever attempted. Scientists are looking for tiny violations of Einstein's equivalence principle, the idea that gravitational and inertial accelerations are indistinguishable. Finding such violations would suggest that our current understanding of spacetime is incomplete, pointing toward theories that unify quantum mechanics and gravity in ways we cannot yet achieve. Space-based experiments extend these investigations into environments impossible to create on Earth. Satellites carrying ultra-precise atomic clocks can measure how quantum effects influence time dilation in the microgravity environment of orbit. The absence of terrestrial vibrations and electromagnetic interference allows measurements of extraordinary precision that reveal subtle aspects of how time behaves in varying gravitational fields. These research programs converge on fundamental questions about the nature of reality that touch on some of the deepest mysteries in physics. How do quantum mechanics and gravity interact when both become important? Is space-time fundamental or emergent? Does consciousness play any role in how quantum systems evolve through time? The answers will likely require theoretical breakthroughs that revolutionize our understanding of how the universe works at its most basic levels. Current theories like string theory and loop quantum gravity offer different approaches to these questions, each suggesting that time's true nature might be far stranger than either classical physics or quantum mechanics alone would suggest. These theories remain incomplete and largely untested, but they provide frameworks for thinking about how time might behave when quantum effects and gravitational effects both become important. The experimental search for quantum gravity effects continues through increasingly sophisticated measurements of space-time fluctuations, gravitational wave propagation, and the behavior of quantum systems in varying gravitational fields. Each advance in measurement precision brings us closer to regimes where quantum mechanics and gravity both matter for determining how physical systems evolve. Perhaps the most profound realization emerging from these investigations is how time's flexibility reveals the universe's fundamental indifference to human intuitions about causality and sequence. We evolved to understand moderate speeds, weak gravitational fields, and familiar temporal scales. When physics takes us beyond these comfortable ranges, our intuitions become unreliable guides to how reality actually operates. The universe unfolds according to mathematical principles that remain indifferent to human preferences while creating the conditions that make human experience possible. Time dilation that would separate interstellar travelers from their home civilizations also enables the formations of stable atoms and the evolution of complex structures like planets and life. The same relativistic effects that make cosmic communication difficult also allow the universe to evolve from simple initial conditions to the rich complexity we observe around us. Understanding time's true nature requires accepting that reality operates according to principles that often contradict everyday experience while remaining mathematically precise and experimentally confirmable. The flexibility of time emerges not as a violation of natural law, but as a fundamental feature of how space-time works, revealed through careful measurement and theoretical analysis that extends our understanding beyond the limitations of intuitive reasoning. The story continues unfolding through ongoing research that pushes the boundaries of what we can measure and calculate about time's behavior in extreme conditions. Each gravitational wave detection, each atomic clock experiment, each advance in quantum technology reveals new aspects of temporal reality that remained hidden from previous generations of investigators. These discoveries accumulate into an increasingly detailed picture of time as perhaps the most mysterious dimension of physical reality, serving simultaneously as the stage upon which events unfold and as a dynamic participant in those events, flowing at rates determined by motion and gravity while remaining woven into the fundamental structure of space-time itself. The universe emerges as stranger and more subtle than everyday experience suggests, yet also more precisely knowable through the mathematical languages of physics that allow us to calculate time dilation effects, predict gravitational wave signatures, and design experiments that probe the deepest mysteries of temporal existence across scales from quantum fluctuations to cosmic evolution. In this vast, quiet expanse where time flows differently for every observer, where past and future lose their absolute meanings, where consciousness emerges briefly to contemplate its own temporal nature, we find ourselves carried along by currents in space-time that operate according to principles both beautiful and indifferent, revealing through their mathematical precision that the universe remains far more mysterious than our brief moment of awareness might initially suggest. The engineering challenges of time manipulation pale beside a deeper mystery that physicists have been quietly wrestling with for decades. Every equation that permits time travel, every exotic solution that opens doorways to the past, carries within it the seeds of logical catastrophe. The universe appears to have constructed itself in ways that make certain forms of temporal manipulation theoretically possible, while simultaneously creating barriers that may be impossible to overcome. Consider the grandfather paradox, perhaps the most famous of these logical puzzles. Travel backward in time and prevent your grandparents from meeting, and you create a causal loop that undermines its own existence. If they never meet, your parents are never born, you never exist, and therefore never travel back to prevent their meeting. The paradox resolves by negating its own premise, creating a logical contradiction that challenges our understanding of causality itself. But this represents just one member of an entire family of temporal paradoxes. The information paradox asks what happens when you travel to the past, carrying knowledge that didn't exist at that time. Where did the information originate if you learned it in the future and then carried it to the past? The bootstrap paradox explores scenarios where effects precede their causes, where consequences create the very conditions that led to them. These aren't merely philosophical puzzles, they represent genuine challenges to the logical consistency of physical law. If backward time travel were possible without constraints, it would create situations where the universe contains contradictory information about its own past. Events could simultaneously have occurred and not occurred, creating logical instabilities that might propagate through space-time like cosmic syntax errors. Some physicists have proposed that nature itself prevents such paradoxes through mechanisms we don't yet understand. The Novikov self-consistency principle suggests that the universe might enforce logical coherence by allowing only those time travel scenarios that are consistent with what we already know happened. In this view, you could travel to the past, but only in ways that preserve the historical record you remember from your original timeline. This principle implies a kind of cosmic censorship where space-time itself acts as an editor, preventing logical contradictions by constraining the actions of time travelers. Perhaps the laws of physics contain hidden mechanisms that make paradox-generating actions impossible, not through external intervention, but through the fundamental structure of causality itself. As you contemplate this possibility, notice how it reveals something profound about the relationship between physical law and logical consistency. The universe operates according to mathematical principles, but those principles must also preserve the logical coherence of cause and effect. Perhaps backward time travel is constrained not by energy requirements or exotic matter limitations, but by deeper principles about information and causality that we're only beginning to understand. Alternative approaches to the paradox problem propose that time travel might split timelines rather than altering them. In this many worlds interpretation of temporal mechanics, traveling to the past creates a new branch of reality where your actions play out without affecting the original timeline you came from. You could prevent your grandparents from meeting, but this would create an alternate timeline where you were never born, while your original timeline continues unchanged. This scenario preserves logical consistency by multiplying timelines rather than contradicting them. Each possible outcome of time travel creates its own branch of reality, expanding the universe into an ever-growing tree of alternative histories. The time traveler becomes an immigrant to a new timeline, forever separated from their original sequence of events. But such solutions come with their own conceptual challenges. If every time travel event creates new timelines, then the universe becomes infinitely complex, branching into countless alternative histories with each temporal intervention. The original timeline becomes just one thread in a vast tapestry of possible worlds, most of which remain forever inaccessible to observation or verification. Moreover, the many worlds interpretation raises questions about personal identity and continuity that extend far beyond physics. Which version of yourself is the real one if multiple timelines contain variants of your existence? How do you maintain a sense of identity across timeline branches that diverge based on the actions of time travelers who may be other versions of yourself? These questions touch on fundamental issues about consciousness and continuity that philosophy has struggled with for centuries. Time travel doesn't just challenge physics, it challenges our basic concepts of identity, causality, and the nature of existence itself. The universe might permit backward time travel only in forms that preserve logical consistency, but preserving logic might require sacrificing other things we consider fundamental to human experience. Current research in quantum mechanics suggests additional layers of complexity that could affect time travel scenarios. Quantum systems exist in superpositions of multiple states until measured, creating probability clouds rather than definite outcomes. If time travel involves quantum systems, which seems unavoidable given that all matter has quantum properties, then the temporal mechanics might involve probability rather than certainty. Perhaps time travelers don't create definite changes to the past, but rather shift the probabilities of various historical outcomes. Instead of preventing your grandparents from meeting with certainty, your actions might reduce the probability of their meeting while increasing the probability of alternative scenarios. The past becomes fluid rather than fixed, shaped by probability distributions that evolve based on temporal interventions. This quantum approach to time travel paradoxes suggests that causality might be probabilistic rather than deterministic. Events don't have single definite causes, but rather emerge from complex webs of probability that can be influenced by future actions. The universe maintains logical consistency, not by preventing paradoxes, but by ensuring that all possible outcomes remain probabilistically coherent. Such scenarios require thinking about time and causality in ways that challenge basic intuitions about how events unfold. We're accustomed to thinking of the past as fixed and the future as open, but quantum time travel might make both past and future probabilistic, with certainty emerging only through the accumulated weight of many overlapping probability distributions. The experimental investigation of these possibilities remains far beyond current technological capabilities. Testing time travel paradoxes would require actually achieving backward time travel, something that may be fundamentally impossible or may require exotic conditions we cannot create. But physicists can explore the mathematical frameworks that govern such scenarios, searching for internal contradictions or hidden consistencies that might reveal whether time travel paradoxes represent genuine barriers or merely apparent puzzles. Some of this work focuses on closed time-like curves, the mathematical structures that would enable backward time travel in general relativity. These curves represent paths through spacetime that loop back to earlier times, creating the possibility of causal loops and temporal paradoxes. By studying the mathematical properties of such curves, physicists can explore what kinds of consistency conditions the universe might impose on time travel scenarios. Recent work suggests that closed time-like curves might naturally evolve towards self-consistent configurations, eliminating paradoxes through the dynamics of spacetime itself. If you tried to create a grandfather paradox by traveling back in time, the curvature of spacetime might respond in ways that prevent the paradox from occurring, perhaps by making it impossible to reach the specific location and time where you could interfere with your grandparents' meeting. This represents a kind of temporal immune system where space-time protects its own logical consistency by dynamically adjusting to prevent contradictions. The universe might be more robust against paradoxes than simple analyses suggest, containing self-correcting mechanisms that preserve causality even when exotic physics creates the potential for temporal loops. However, such mechanisms remain speculative, requiring theoretical frameworks that unify quantum mechanics and gravity in ways we cannot yet achieve. Understanding how space-time might protect itself against paradoxes requires understanding how information and causality operate when quantum effects and gravitational effects both become important. The intersection of quantum mechanics and gravity creates additional puzzles about time travel that go beyond classical paradox scenarios. Quantum systems can become entangled across arbitrary distances, sharing correlations that appear to transcend normal space-time limitations. If time travel involves manipulating quantum entanglement, it might create forms of temporal correlation that classical physics cannot describe. Imagine entangling particles across time rather than space, creating quantum correlations between past and future events. Such temporal entanglement might enable forms of information transfer that bypass the usual limitations of causal propagation. Quantum mechanics already permits correlations that seem to operate faster than light across spatial distances. Perhaps it also permits correlations that operate backward in time across temporal distances. But quantum entanglement cannot be used to transmit information in any conventional sense. The correlations it creates are statistical rather than deterministic, appearing only when many measurements are compared rather than being accessible through single observations. Temporal quantum entanglement might face similar limitations, creating correlations between past and future that cannot be exploited for practical time travel or communication. These quantum aspects of potential time travel scenarios remain largely unexplored because they require theoretical frameworks that don't yet exist. Understanding how quantum mechanics and gravity interact in time travel scenarios requires solving the problem of quantum gravity, one of the most challenging frontiers in theoretical physics. Current approaches to quantum gravity, including string theory and loop quantum gravity, each suggests different possibilities for how time might behave when quantum effects become important. Some theories propose that time itself might be quantized, existing in discrete units rather than flowing continuously. Others suggest that time might be emergent, arising from more fundamental quantum processes rather than being built into the basic structure of reality. If time is quantized, then time travel might involve discrete jumps rather than continuous motion through temporal dimensions. If time is emergent, then time travel might require manipulating the quantum processes from which time arises, rather than moving through a pre-existing temporal landscape. These possibilities remain deeply speculative, but they suggest that our current understanding of time travel limitations might be incomplete. The search for experimental evidence of quantum gravity effects continues through increasingly sensitive measurements of space-time fluctuations and gravitational phenomena. While we cannot directly test time travel scenarios, we can probe the fundamental nature of space-time in regimes where quantum mechanics and gravity both matter for determining how physical systems evolve. Some experiments search for violations of Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant velocities. Finding such violations could suggest that space-time has a more complex structure than general relativity describes, potentially opening new possibilities for temporal manipulation. Other experiments measure how quantum systems behave in varying gravitational fields, looking for deviations from Einstein's predictions that might point toward quantum gravity effects. These measurements probe the intersection between quantum mechanics and gravity in controlled laboratory conditions, revealing how these fundamental forces interact when both become important. The accumulated results from these experiments continue to confirm Einstein's predictions while pushing measurement precision into regimes where quantum gravity effects might become observable. Each advance in experimental capability brings us closer to understanding how space-time behaves at the scales where time's true nature might be revealed. Perhaps the most profound insight emerging from studies of time travel paradoxes is how they reveal the deep connections between physics, logic, and information. The universe operates according to mathematical laws, but those laws must also preserve the logical consistency of cause and effect. Paradoxes represent situations where mathematical possibility conflicts with logical coherence, forcing us to consider which principle takes precedence. Current physics suggests that logical consistency might be the deeper principle, constraining what kinds of mathematical solutions can be realized in nature. The equations of general relativity permit closed time-like curves, but the universe might contain additional principles that prevent such curves from creating logical contradictions. Understanding these principles requires grappling with fundamental questions about the nature of information, causality, and the structure of physical law. How does the universe maintain logical consistency? What mechanisms prevent contradictory information from propagating through spacetime? How do quantum mechanics and gravity interact to preserve causal order? These answers remain among the deepest mysteries facing physics today. We cannot yet definitively say whether the universe permits the kind of backward time travel that creates paradoxes, or whether hidden mechanisms in the structure of spacetime itself prevent such contradictions from ever arising. Current models suggest that nature might indeed have built-in safeguards, quantum or gravitational principles that preserve causality, even when exotic physics creates the mathematical possibility for temporal loops. What we can say with confidence is that time is far stranger than everyday experience reveals. Forward time travel through dilation effects happens continuously around us in GPS satellites, cosmic ray particles, and atomic clock experiments that measure temporal variations across distances as small as millimeters. The universe demonstrates every moment that time really is personal, flowing at rates determined by motion and gravity in ways that challenge our deepest assumptions about temporal experience. Backward time travel remains deeply uncertain, perhaps forever beyond reach, not because of engineering limitations alone, but because the universe might be structured to prevent logical contradictions at the most fundamental level. The same mathematical elegance that permits exotic space-time geometries might also contain principles that preserve causality and prevent paradoxes through mechanisms we do not yet understand. Perhaps the most profound realization is how studying time's nature reveals the universe's indifference to human intuitions while simultaneously creating the conditions that make consciousness possible. We are temporal creatures embedded in a cosmos where time flows differently for every observer, where simultaneity becomes relative, where the steady tick of seconds that feels so absolute dissolves into a complex web of personal time streams flowing at rates determined by motion and gravity. The universe unfolds according to mathematical principles that remain beautiful and precise while operating beyond the scale of human experience, revealing through careful measurement that reality extends far deeper than our brief moment of awareness can fully comprehend. In this vast, quiet expanse, where time itself becomes fluid, we find ourselves carried along by currents in space-time that have been flowing since the beginning of everything, carrying each observer through their own unique sequence of moments in the endless, silent dance of existence.